Good afternoon, ladies and gentlemen. Welcome to the final joint Heidelberg Astronomical Colloquium of this semester, and we are very privileged to have a special guest here as the final speaker, Lisa Kewley. I'll just pass over to Ralph Klessen to make the formal introduction.
Okay, thank you. Thanks, Richard. Of course, thanks, Lisa, for coming to Heidelberg for this final colloquium in the winter term. Let me introduce the speaker. Lisa is Australian. She studied and got her PhD. She got her PhD at the Australian National University. Then she got the CFA fellowship, which brought her to Harvard in Boston on the other side of the Pacific. After that, she obtained a Hubble Fellowship, which she brought halfway back home to Hawaii. And she was working for a few years then at the Institute for Astronomy in Honolulu. In 2011, she went back to Australia, to the Australian National University, to Mount Stromlo, the research school for astronomy and astrophysics. She became, in 2017 until 2022, the director of the Australian Research Council Centre of Excellence in All-Sky Astrophysics in 3D, which is a long name, so it's better known as Astro 3D. And so this is indeed like the excellence clusters which we have here in Germany. So this was, I think, lots of work and lots of cool research that is done. In 2022, she moved to the Center for Astrophysics at Harvard University and the Smithsonian Institution as the new director and the first female director. And I think that is very much needed to bring some fresh wind into a old and scientifically super productive institution. Let me say a few words about the science. So Lisa got her PhD about the connection between star formation and supermassive black holes. And in a sense, she continued working on that, and she looked at line ratios of diagnostic emission lines, H alpha, H beta, oxygen 2, 3, sulfur lines, and so on. And if you ever plot these lines against each other, you will realize there is the Kewley line that is a demarcation line between, you know, the standard star formation line ratios and those that are more, let's say, consistent or physically motivated by active galactic nuclei, so by the accretion onto a supermassive black hole and the accretion disk around it. She has received many honors and prizes. So, for instance, in 2006, the Annie Jump Cannon Award of the American Astronomical Society, or the Newton Lacy Pierce Prize. She is member of the National Academy of Australia. She is member of the National Academy of the US, of Academy of Sciences, and the Academy of Arts and Sciences. Maybe you need to explain the difference at some point. She got a super prestigious ARC Laureate Fellowship, which is like an ESC advanced grant in Australia. And we will learn more about the cool research that she is currently doing and has been doing. So many thanks, Lisa.
Thank you, Ralph. Okay, so today I'm going to be talking about our new photoionization models, and this is work that we've been doing over the last, I would say, about 8 years, and it's almost coming to fruition now. So some of the work I'm about to show you is hot off the press. Some of it is just about to be published and isn't quite published yet. And then finally, at the end of my talk, I'm going to give you a little bit of an overview of all the exciting things that we're doing at the Center for Astrophysics in Boston and what's actually taking up most of my time, not photoionization modeling. So this is a quick summary of the talk today. I'm going to give an overview of the models, and then I'm going to have a little bit of a discussion about the model inputs and the advantages and disadvantages of the different codes. And then I'm going to show you our work over the last few years towards more self-consistent H2 region ISM modeling. And then I'm going to describe our next generation photoionization models, which are about to be released. So this is a little flow chart of how we would get a theoretical spectrum for an H2 region or for a galaxy. And so what we do is we input a stellar atmosphere model and stellar tracks into stellar evolutionary synthesis models, and then that produces a theoretical ionizing spectrum, which we then put inside a photoionization model. And the photoionization model requires a dust model, and then we run the ionizing radiation field through the nebula. We calculate the detailed radiative transfer and the dust physics, and then out of that model, we produce a theoretical emission line spectrum. And so it sounds pretty simple, but it's not. There are a lot of input parameters, and so we need to make assumptions about all of these things. So we need to assume the IMF, the stellar population age, the star formation history, the metallicity in both the evolution synthesis models as well as the photoionization model. We also need to assume an ionization parameter, ISM pressure or density and temperature, and geometry. And so each of these things can play a big role in actually what emission line spectrum you get out. So I'm going to focus on the top part of this flowchart first. And so one of the major problems with this type of modeling is that we are assuming an ionizing radiation field using a stellar evolutionary synthesis model. And these are actually these are the least known parts of our models. In particular, the stellar atmospheres are very difficult to model around stars. And our emission lines that we're producing, and particularly the strong optical emission lines, they're very sensitive to a part of the ionizing EUV radiation field that is actually very, very sensitive to the stellar atmosphere models themselves. And so our predictions of the emission lines can vary critically depending on what stellar atmosphere models we use, the stellar age. The models over there in the figure, the different colors correspond to different ages. And although this is log scale, so a little difference is actually a lot of difference and can make a big difference in how much emission lines we get in each of the ionization states of the different chemical elements there. It's also critically dependent on the metallicity itself. And so the colors now correspond to metallicities, and they vary very dramatically also with metallicity. So we need to ensure that we've got consistent metallicities going in with the stellar evolutionary synthesis models and the photoionization models. Now, I'm often asked about stellar tracks and what impact stellar tracks have on the optical diagnostic diagram. So in the figure there, we have various emission line ratios. We've got oxygen 3 and H beta on the y-axis, and then we've got N2 and H alpha on the x-axis. And the different models, the different plots here just show you different models with different stellar tracks. In the top, we've got Geneva and the Padova tracks. And then we also, at the bottom, we're just comparing Starburst 99 with SLUG, which is a stochastic star formation code. And so there's actually very little difference between the different stellar tracks and between whether you use stochastic and non-stochastic sampling, at least for these optical diagnostic lines. The one big problem that we have is the abundance sets, and this has been an ongoing problem for a long time. We finally are able to overcome it. So the various different stellar evolution synthesis models before, they assumed what we would consider quite an old abundance set, and an abundance set is the relative ratio of the different chemical elements relative to each other and how they change with metallicity. And so what was assumed is that we would take something like Anderson-Graves abundance set. So they basically assume a set of solar abundances, and then you scale everything up and down with solar, with the exception of nitrogen and carbon, which have both a primary and a secondary nucleosynthetic origin. So this just assumes that all the elements scale with each other, except for nitrogen and carbon, with a constant amount. And we can see from data that that's actually not true at all. So if we take Milky Way H2 regions and stars, and you can plot their actual measured abundances here. So this on the green here is argon to oxygen, and in the blue is neon to oxygen. And that's shown on the x-axis against metallicity. And you can argue that argon, indeed, the argon to oxygen ratio is flat. And so that actually, you can assume that that's constant with metallicity, but neon to oxygen absolutely isn't. And then on the right-hand plot there, this is chlorine to oxygen. The Anderson-Graves value is shown in the dashed line, that's black, but the data is actually completely off that line. So it's actually not accurate at all, and should be actually lower in reality. And so what David Nichols did, who was a former PhD student of mine, now a postdoc of mine, is that he calculated all the different abundance ratios, relative abundance ratios, using known H2 regions in the Milky Way and the LMC and the SMC. And he also used stellar abundances as well to produce a realistic abundance set that then changes with metallicity in a way that's actually observed, rather than making this assumption. And it makes a very big difference on optical diagnostic diagrams. This diagram is a really useful diagram. It's oxygen 3NH beta on the y-axis, which is very sensitive to ionization parameter, which tells you about the amount of ionizing photons produced by the radiation field. And the nitrogen 2 to oxygen 2 ratio on the x-axis, which is sensitive to metallicity. And so if you make a plot of this, what you expect to see is a variation depending on ionization parameter and metallicity. And so the gray dots here are Sloan Digital Sky Survey data, and the data that comes up off the top and goes vertical, those are AGN. So we don't need to model those. We use different models for the AGN. But what we care about is this long curve, which are star-forming regions, so the long diagonal line there. And this, we need to be able to reproduce all of those data points. And the problem is that the previous uniform abundances, which in the right-hand plot there are black and blue and green, they're really kind of crunched up. And you can see it here in the left-hand plot in black. And they don't actually cover the full range. They don't cover the lowest metallicities, and they don't cover the highest metallicities either. And so the only one that actually is able to account for all of the data is actually David's galactic concordance non-uniform abundance sets. And so we've now updated our photoionization models with this galactic concordance abundance set. But the problem we had is that the stellar tracks in the stellar evolution synthesis models still use the Anderson-Graves models. And so for years, this is what was actually happening. So now, Katie Grasher, who is a postdoc of mine, she is working on stellar tracks, a whole bunch of different sets of stellar tracks. And this is the ones that have just been produced called Stromlo stellar tracks. And these are based on those galactic concordance abundances. And she calculated stellar tracks as well as opacity tables, and then we put those into our stellar evolution synthesis models. And the different colors up in these figures show you the different tracks. So we've got galactic concordances in the purple and pink colors, and then the Anderson-Graves are in the bluish to green colors. And you can see there's actually really very little difference at iron to hydrogen ratios of 0. That's in the log. But if you use, if you go to the lower metallicities there, you actually do see a larger difference between those different stellar evolutionary tracks. And so we can have a look at what they look like on the ionizing radiation field figures we showed earlier. So the previous one we had is on the left, and the one with the new galactic concordance abundances is on the right, which is a zoom in on that main part of the wavelength range that we're interested in, which is where our key optical emission lines are produced. And you can see the impact of these also if we look at the predicted EUV radiation, and as a function of age. And again, the main difference occurs at the very low metallicities on the right-hand side there. So the solar scaled abundances give quite different ionizing photon luminosities than you'd get if we use the galactic concordance abundance sets. What Katie's doing now is having a look at the impact of these on emission line ratios. And so the figure, the spectrum there at the top shows you the difference between the galactic concordance metallicities, which is in purple, and the solar metallicities, which is in black. And you can see it's made a difference to the H alpha, but and also the sulfur 2, or relative to if we just assume that the continuum is normalized for each of those. what it actually impacts is the relative amounts of ionizing photons that's producing the emission lines, and then that makes an impact on the emission line spectrum that comes out of the photoionization models. What she's doing next is using chemical abundance ratios from hydrodynamic chemical evolution simulations, and she wants to do different stellar tracks for different redshifts so that we can actually model accurately the stellar abundance sets at different redshifts based on those models, and then to see if that's going to make an impact on the chemical abundance diagnostics that we produce out of those different models. Okay, so that's work that we've done there. We're now going to move on in the talk to what we've been doing for our photoionization models. And I'm really excited by this work because this has been a long time coming. It's several years worth of work and a lot of work by a particular grad student of mine, Yufei Jin. So there's lots of different choices of photoionization models, and these are the main ones. So we have mappings photoionization models, and then we have the cloudy photoionization models. Those models they compute detailed radiative transfer and typically complex dust physics for around 30 elements. And their focus is actually on obtaining the correct nebula temperature and density structure. And that's able to vary throughout the nebula, although it's not always done when people run the models. And then you have different types of code here, Moccasin and CM Maclonize, which are Monte Carlo simulations. And so they're ray tracing. They trace photons through a nebula, but they have smaller numbers of elements and simple prescriptions of the physics. So they don't have the detailed radiative transfer processes that are in the photoionization models. This is a problem. Our ideal model combines the two. And so that's what we're doing now. Just in case you were wondering, lots of people wonder how do mappings and cloudy compare. We've done lots of comparisons through the years, and we always get this type of result that they don't really change very much if you give them the same inputs. About 0.1 dex on average is difference, and the main difference is often due to the different atomic data sets that are being used in the models and how up to date each of these are. And so what typically happens is mappings will update its atomic data and then produce a little bit different estimates of the oxygen lines and nitrogen lines, for example. Oxygen's changed a bit over the last few years, and then cloudy will update, and then there'll be another update, and each model goes steps forward like that. Now, there's advantages and disadvantages of using these photoionization models. So, as I said earlier, we can produce accurate temperature and density structures through the nebula, assuming that the nebula is uniform. And we can also, these are fairly applicable to H2 regions and galaxies if you're looking at a global spectrum, but it's not very good if you're looking at spectra across galaxies with integral field data, which is what we've got now. The disadvantages are that they're very sensitive to the stellar atmosphere models, which I talked about earlier. The dust depletion factors were not very well constrained, and the codes are limited to spherical or plane parallel geometry, which I consider the main problem with the models. So work that we're doing for dust depletion factors, we're doing a thing that we call hyperspectral imaging of observations of H2 regions. And what this means is very, very, very high signal to noise integral field spectroscopy of nearby H2 regions in the Milky Way and the LMC and the SMC. And we're doing it at the Siding Springs 2.3 meter telescope. And this is work started by Mike Doppiter there, who's standing next to the WIVES spectrograph, which he designed and built. And he is very, very proud of his spectrograph. Unfortunately, Mike Doppiter's no longer with us, but we're carrying on his research. Now, I should say that when we go observing in Australia, it's actually a very dangerous activity and sport to do, because we have dangerous spiders. This is a redback spider. You actually see them a lot of places in Australia. This is a red belly black snake. We have them hanging out outside the observatories. This is a brown snake, very, very poisonous snake. My son told me the other day that he nearly stepped on one. And I wish he'd told me at the time. And we have very dangerous koalas that they're called drop bears. And if they fall out of a tree on you, they're actually territorial. And if they fall out of a tree on you, it can be very dangerous. So you think koala bears are nice and fluffy, not drop bears. We also have bushfires. And in fact, these telescopes at Siding Springs have survived a bushfire. The bushfire went around and over the telescopes, and we have very clever coatings of paint on the telescopes which actually prevent the fires from going inside. And then we have very dangerous kangaroos as well, which you've probably heard of. And so with this, you know, it's lucky we survived, really. So here's what we got after those observations. So this is a spectrum of Orion. And we did integral field spectroscopy of Orion. So we actually have, you know, hundreds of spectra of Orion and different parts of Orion. And every single line you see here on this figure is not noise, it's a line. And so you can zoom in. Let's take that bit and keep zooming in. And so there's so many lines here that you can actually use the models to work backwards and to constrain the dust depletion factors, because you've got so many lines in the spectrum. And so this is a very beautiful technique. And this is work that David Nichols and Ralph Sutherland are continuing for Mike. Now, we're also limited in these codes to spherical and plane parallel geometry. So all the codes all the models we produced in the past have been either spherical or plane parallel. And one of the problems is that H2 regions, they're often assumed with those spherical or plane parallel models to have a constant density and temperature distribution. And so, for example, a lot of diagnostics that you use make this assumption. So if you're using a sulfur 2 Osterbrock density diagnostic or an oxygen 2 density diagnostic, or you're using the auroral lines to calculate temperature, they all assuming either constant density or constant temperature. And so it's actually not correct. And when we allow the density and the temperature to vary through the models, we get something pretty different. So these figures here show you that on the top panel are temperatures for different metallicities, and on the bottom is densities for different metallicities. And you can see here that not many of them have a constant density or temperature really across the whole nebula. And so we've got thickness of the nebula on the x-axis, and most of them actually vary with distance. And there's so maybe metallicity of 8.23 in log ONH would be constant. That's about it. And then the question is, do these actually look like observations? Do these temperature and density distributions we get, assuming the spherical geometry, are they actually right? And so with Orion, no, they don't look anything like it. So these are the temperature and density distributions we get just through one, you know, if we just take one axis in Orion, you can see that the density is varying and the temperatures varying. And in fact, the electron density varies from 600 centimeters per second down to, you know, well below 100 centimeters per second, more like 30. And here actually that's centimeters per second cubed. And the two different colors here on the left-hand side show you two different ways of measuring the electron temperature structure there. And they both give quite different results as well. And neither of them are actually constant with distance across the nebula. So then we started looking at other H2 regions. So these are also observed temperature and density structures of nearby H2 regions. Again, using WIVES on the 2.3 meter telescope, and the emission line maps here on the left and on the right. What's really interesting is the top panel here shows you the electron temperatures calculated using 3 different methods. This is for the same H2 region, and on the bottom are 2 different electron density measures using on the same H2 region. And, you know, they're pretty different. And also there's a lot of variation. It's certainly not constant across this H2 region. You've got regions of very high density in sulfur 2, regions of higher density in oxygen 2, but less dense than the sulfur 2 regions. And then in the electron temperature zones, it's very different depending on which emission line you're using, and that's because the lines are produced in different parts of the nebula. And so your oxygen 3 is produced much closer to the ionizing sources, and we have oxygen 2 being produced further out in the nebula. It's produced in a similar zone to nitrogen 2, but they have quite different maps. Now, this is another figure which shows 4 different H2 regions, so you can see how different they are from H2 region to H2 region, and the electron temperature, and here calculated, you can see them across. They're calculated all using the oxygen 3 line on the bottom, the oxygen 2 in the middle, and the nitrogen 2 in the top. And again, we get quite different geometries, but they're certainly not constant. And so then the question is, are our models that we have with a spherical geometry, are they able to produce these temperature and density distributions that we see? Answer is no. So the observed data is in red or green or blue, depending on which way we've got of measuring the electron temperature and density, and then the models are in black. And so they're really not doing very well at all. And we think this is because we're assuming a spherical cow, basically, for our H2 regions. And we know that when we look at the H2 regions, they're just not spherical. They're not plane parallel. And they can be sort of blister-like, or they can have cone geometries and other types of structures. And so they're actually very complex. And so this is what led us to doing our Monte Carlo radiative transfer code. And so this is Yefei-Jin's thesis, the culmination of his thesis, where we're combining the full Monte Carlo radiative transfer techniques with our mappings photoionization code of 30 elements. And so we're able to now reproduce the emission line spectra for 30 elements. And we've got the full treatment of the radiative transfer cooling and heating processes for those elements, and we're able to produce an accurate geometry. So we use a fractal geometry with a log normal density distribution, and the figure on the right just shows you cuts. So, you know, cuts through this nebula, and you can have a look at each of the emission line plots in H beta in the top and oxygen 3 in the middle and nitrogen 2 on the bottom. And these are much more similar to what we had with what we actually observe with our nitrogen 2 and O3 and H beta. At the moment, these are fairly simple models because we're testing them. We're assuming a central ionizing star with an effective temperature of around 40 kilokelvin, and ISM abundance is solar metallicity, and then we're assuming radiation bounded for these particular models. And this is the images that we get. The ionization parameter is shown at the top, and temperature and density, and all various different emission lines. What's really interesting about this is that if we compare our uniform geometry spherical models with our 3D Monte Carlo fractal geometry, then we know we can actually see what the impact is on the emission lines that we produce. And so the top right-hand figure there shows you the emission lines where we're dividing the flux of the 3D Monte Carlo models with the 1D photoionization uniform models. And you can see that some elements, so the Balmer lines makes no difference, but it actually makes a very big difference for lines like sulfur 2 and oxygen 1. And the reason for that is because they're boundary elements. They're produced at the edge of a nebula. They require a harder ionizing radiation field to produce. And if you have at the edge of the nebula, typically only the photons that are left are if you've had a hard radiation field there, what's still there. And so you have sulfur 2 and oxygen 1 being produced at the very edge of the nebula, whereas lines like nitrogen 2 is produced a little bit further in, and oxygen 3 can be produced throughout in this particular nebula. And so really big difference in the predictions of the optical emission lines when you start using the 3D Monte Carlo radiative transfer. And this shows you differences in the geometry. So this is using exactly the same radiation field and all the same parameters with the exception of geometry. And so with the spherical model is on the right and the fractal model is on the left. And you know, it's pretty obvious that we've got a more realistic look on the left-hand side for these line ratios. Now, some of these line ratios are really important. The R2-3 line ratio on the bottom left is a typical metallicity diagnostic. And so this means that metallicity diagnostics calculated using the spherical models are going to be different to what we get using the 3D Monte Carlo models. And same with the ionization parameter diagnostics, which is in the bottom right-hand side. And that's just due to where the lines are being produced in the nebula. And what's happening in the fractal geometry is because you've got different pockets of density, you've got various different lines of sight, and some of them are able to travel a long distance to get to a parcel of gas, whereas they can't if you have a spherical uniform geometry. And because they can travel a long distance, what that means is that your effective area over which you're able to produce those sulfur 2s and oxygen 1, so the perimeter, and not a perimeter of a circle, but the perimeter around your density distribution is larger. That means you get more oxygen 1 and more sulfur 2. Your area that you're producing the oxygen 1 and sulfur 2 is larger in these 3D simulations. Now, this is comparing the integrated emission line spectrum. So you just average over the whole nebula. And this is similar to what we get if we're putting a slit or a fiber on an H2 region. You just get an integrated spectrum of that H2 region. And on the right-hand side is a comparison of the flux with map on the y-axis with our previous geometry. So this is the uniform spherical geometry. And then the fractal nebula is on the x-axis. And so you can see where the different emission lines, how much they're varying. The oxygen 3 is shown as well as sulfur 2 and nitrogen 2, but a lot of the lines are actually indeed different. And these are the optical diagnostic diagrams. So I showed you that earlier, those diagrams earlier. This is all models. So the black here are the Monte Carlo simulations, fractal simulations. And so they actually, I'm not sure if you can see it at the back, but they actually come all the way down here and they all go all the way up there. So we're actually able to reproduce the curve. And we do see this in H2 regions and across galaxies. If you plot all the H2 regions you observe in a galaxy on these diagrams, you see this sort of distribution like this. Whereas a spherical equivalent model doesn't actually span a very large range in these diagnostic diagrams. So we think we're able to finally start sampling the full range of emission line ratios that you would expect to be getting in across an H2 region or perhaps even across a galaxy. And so this is what it looks like. This is what we've been doing over the last few years looks like. So first we looked at the SMC, LMC and Milky Way H2 regions. And we use those to derive the galactic accordance abundances, and we're using them to derive the dust depletion factors and the geometry. So these are really data-driven models now, or you could call them evidence-driven models. And we used that abundance set to produce the new stellar tracks, which then got put into the stellar atmosphere models and the stellar evolutionary synthesis models. And then finally, we're able to reproduce the 2D photoionization models and the 3D photoionization models with the fractal geometry. And so doing that comparison between them has been really illuminating. And the next step now for these models is to run a large suite of models for many different geometries. We want to put star clusters. These ones I showed you just had single stars in them. We did observe single star H2 regions, so this comparison is legitimate, but where we want to be comparing with other H2 regions out there and large samples of H2 regions, we actually need to have, star clusters in those models as well. They are computationally intensive, and so we want to be having supercomputers running on these all the time. So what's next for these models? So we're now using them to calculate new self-consistent diagnostics using the fractal models for the H2 regions and star-forming galaxies. I haven't talked much about AGN, but I'm going to give you a sneak preview on our AGN modeling in the next couple of slides. And the ultimate goal is to then be able to use these new self-consistent diagnostics. And so they've been upgraded in many different ways, right? So we've updated the metallicity abundance sets, the dust depletion factors, the stellar evolution spectra that we put into our models, and then we've updated the geometry in the models as well. And so with these new diagnostics, what we'd like to do is a co-moving star formation and metallicity history of galaxies using JWST and ground-based data. And we're also working on AGN diagnostics, because at the moment, when we're doing star formation and metallicity histories, we throw out all the AGN because we can't use our diagnostics to measure metallicities or star formation on them. They're just removed. But, you know, they exist in the universe and we shouldn't be throwing them out because we're not actually really sampling the whole star formation history or the whole metallicity history if we're using emission lines to derive these things. And so this is work being done by my student, Pei-Xin Zhu, and she's using AGN models to derive metallicity diagnostics. And these are some sneak previews of these diagnostics. There's some really good diagnostics there's one in the UV, which is very nice. This is based on the nitrogen 3 and oxygen 3 line. And then the nitrogen 2 and oxygen 2 line in the optical is also, and in the UV are actually quite good diagnostics for metallicity as well. And the colors correspond to ionization parameter. So you don't want these varying very much with ionization parameter. She's also calculating metallicity diagnostics in the infrared band, and the paper's is almost ready to submit at the moment. So there's also some good diagnostics in the infrared. And then what we plan to do with this is to apply all our new diagnostics to JWST data. So this is a mappings prediction of a spectrum of a Z of 9 star forming galaxy. Right now, we just have photometry of the highest redshift galaxies, but we're anticipating with follow-up observations, we'll be able to get spectroscopy of these galaxies, and particularly in the UV with ground-based observations. And some of those are going to wait till the ELTs are on board. And so we have your EELT is going to come online quicker than our EELTs in the US. And but we at the CFA and in Australia are heavily involved in the Giant Magellan Telescope project and are building instruments for those telescopes. And for this particular work, what's very exciting is the GMTIFS spectrograph, which is it's a near-infrared emission integral field spectrograph, and we are going to use that to derive, data from individual H2 regions for galaxies at intermediate redshifts. So for those of you who aren't familiar with galaxies at various redshifts, this prediction of this galaxy at redshift 1.5 right now, and what that H alpha map looks like, that's what we currently get for a nearby galaxy. And we can't possibly get that for a galaxy at Z of 1.5. But with GMTIFS, we'll be able to push out in redshift and to do some of these studies of H2 regions and looking at things like metallicity distributions and electron temperature distributions at high redshifts than we possibly can at the moment. Gee, I hope that Athena X, or I wish Athena X would go ahead, because for this type of work, Athena X would be amazing. So I've had this slide around for a while, and Athena X is going to be able to measure, I don't know what the status of Athena X is at the moment, whether it's been canned or not. I keep hearing rumors. But it could measure the temperature and the metallicity and the density in galaxies and clusters in all these different elements, like calcium, neon, nickel, magnesium, sodium, aluminium, all these things we can't do at the moment. And constraining AGB and supernova yields, this would be amazing for doing chemical histories of clusters in multiple elements. And so I really, really, really hope that Athena X gets going, because I think this would revolutionize this type of work. And so what I want to conclude about our photoionization models is that the next generation photoionization model is coming. It's called Mcubed, and the papers, there's 2 papers already published by Yifei Jin. The next one is just been accepted, so it'll come out on the archive shortly. And then in the coming year or 2 years, once we've fully tested it on H2 regions, then it's going to be made available to the public, and you'll be able to go and download the model and run it yourself, as well as the different pre-run grids that we're calculating at the moment. Finally, in the last few minutes, I just want to talk about what I'm currently spending most of my time on, which is being director of the Center for Astrophysics, Harvard and Smithsonian. And you might not be aware that it has 850 people, making it the largest astronomy institute in the world. And we're spread over 4 buildings. And so this is a problem for us. We would like to have 1 building. We have telescopes all over the world. So we've got telescopes, sub-millimeter array in Hawaii, as well as a partnership for the multi-mirror telescope in University of Arizona, and then the Greenland telescope in Greenland. And we also do have running the Veritas telescope also in Arizona. And then we're a partner of the Magellan Telescope project as well. We just celebrated the 23rd anniversary of launching and deploying Chandra satellite, and we're operating the Chandra X-ray Center as well as the data center. And so one area of research that's we've made major advances on and recently is our understanding of black holes. And this is their potential CFA-led flagships in black holes. So this is a key science area for us. Includes a few different telescopes, which I'm going to briefly talk about, but we're really trying to answer some of the main questions in understanding black holes, including how did they form in the early universe and how did they evolve across cosmic time, how did they accrete their material, and what's their impact on their surrounding host galaxies and the ISM. And so we were leading the Event Horizon Telescope project, which made this beautiful image of the center of our Milky Way galaxy. And we're now looking at expanding this and putting more radio telescopes around the world in order to get higher resolution data of the gas falling into the black holes. And also we want to make movies. So we want to actually take the data and do it in time series so that we can actually see how in time the gas is falling into the black holes. And so here the blue points show you the existing radio telescopes that are in the network for the Event Horizon Telescope projects, and the red show where we want to put telescopes. And we've started acquiring telescopes. Some will need to be built, some can be moved. We're doing a reduce, reuse, recycle on old radio telescopes, which is good, and funding agencies, we think, will like it. So we purchased 3 BIMA telescopes. I don't know if you might have heard, some of you might have heard of the old BIMA array. And so they're going to join our SMA and Greenland telescope as part of that network. And they're going to South America and also Tanzania. You might not be aware that Center for Astrophysics is about to do climate research, climate and pollution research. And so this is obviously directly applicable to us as humans, and it's relevant to the average person on the street. And so this is TEMPO. This is a satellite that it's a NASA satellite that we've built and is about to be launched. First week of April is actually April 10th is the launch date at the moment. And this is a US pollution monitor, and it's going to have unprecedented resolution of pollution. So it's going to be hourly monitoring of pollution, but also with a 2-mile radius. So that's like a 5-kilometer radius. And so we're developing an app for mobile phones, so kids at school or anybody really will be able to look on their phone and see how the pollution is right now above them. Go somewhere else, maybe you want to stand outside a factory or whatever, go to the city, go to the country, and you can actually see what the pollution is in real time. And so this is what it's going to be doing. It's going to be making a map. And in particular, it's going to be looking for things like ozone and aerosols and nitrogen dioxide. We also have another satellite called MethaneSat. This is a collaboration between Smithsonian, Harvard, NASA, and the Environmental Defense Fund, which is funded by Jeff Bezos. And this is is interesting because it's a joint NASA philanthropy run satellite, and it's going to be launched not this year, actually. It says due for launch 2023. We just found out that the launch date's been pushed to early 2024. And this one is going to be monitoring methane. So again, it's going to be hourly monitoring of methane over the US with unprecedented resolution. And this is really to help our understanding of climate research and the theoretical modeling of that. We're also developing probe proposals at the moment in the X-rays, and this one's called ARCUS. And so ARCUS is actually, what I like about it is that we're transferring technology from microelectronics industry into X-ray science. So the parts of the detectors come from microelectronics. Interestingly, microelectronics actually took expertise and technology from X-ray detectors, then improved them, and now we're kind of taking that technology back into the next generation X-ray telescopes. And this is really aimed at looking at the missing baryons and metals, and then black holes and how they impact their surroundings, as well as stars and stellar systems. So it's quite a broad range of science for ARCUS. And then we have another probe proposal that we're working on called LEM, which is going to be looking at oxygen, carbon, and iron in our Milky Way. So I think this is fabulous, obviously, because of the chemical elements here. And these are simulations on what we think LEM might be able to observe. And then finally, we would love to build LINX. So LINX is an X-ray observatory, one of the great NASA missions. The timescale for this is likely to be something like 10 years away. But it's pretty cool because it has this X-ray microcalorimeter proposed, which is going to allow sound wave mapping from black holes with sort of a resolution of speeds of 30 kilometers per second. And it's going to be able to, with a high-res imager, we hope, detect black hole seeds in the early universe, which would be really exciting. Okay, so I'm going to finish there and let people ask questions. Thank you.
Thank you very much for that insight into exciting things going on across the Atlantic Ocean, and but very, very especially for this insight into this whole field of diagnostic spectroscopy. And I think we're all very grateful that you've shown us what's going to happen there, and we should actually take a lot of note of that and put it into all the work we're doing right as soon as possible. I'm sure that there will be questions. I'd like to open the questions from the floor here.
Thank you very much for a very interesting talk. And as somebody working on hot star atmospheres, thank you very much for emphasizing how important they actually are in these models, which brings me to my question. You glossed a bit over it when you said that you already calculated new atmosphere models based on the concordance track. So what regimes do they cover so far? Is there something, and what actually are you assuming for the wind mass loss rates, which highly determine the helium-2 ionizing fluxes and above?
Yeah, absolutely. So we're at the moment, we're just doing the high mass stars, and that's because we're most interested in the ionizing radiation field and producing these emission lines, the optical and the UV emission lines primarily. And for consistency, because we're comparing with our previous models, we're inputting those into Starburst 99 and WM Basic, because that's what we did before. And so we're just using exactly the same input parameters as we did. And in future, what we'd like to do, and we've been talking about using some more modern, which are upcoming stellar evolution synthesis models, which have rotation and binary stars. But at the moment, we don't have those in them either, but it's just the standard Starburst 99 models. Yeah.
Okay, thank you.
Hi, I was very interested in the plot you showed by Katie Garasha, where we saw by how much the predicted line flux actually varied depending on our assumptions. So I was wondering, in terms, if we are trying to use the H alpha flux to predict star formation rates, then that should probably have quite large uncertainties associated with it based on this.
Yes, so that will depend on metallicity. So at the very lowest metallicities, that's where we see that large effect. But at the high metallicities, there's actually no effect. So yes, the plan is to derive new star formation rate diagnostics that take that into account, and there'll be a metallicity correction parameter in there as well.
That makes sense. Thank you.
Hello, thank you for a nice talk. I have a question regarding the fractal models that you were showing. the underlying geometry, what is that based on? And does that encode both temperature and density, or just density?
It's just density.
And it's
Yeah,
based
so
on,
it's a log normal density distribution. I can't remember the other parameters, but they're in your phase already published paper. So if you, I really strongly recommend you take a look at it, because he's got all the equations in there as well. It's kind of reproducible if you wanted to do it. And so we're very open with how we're doing the models. Yeah.
okay, thank you.
I don't see any questions on Zoom yet. Any further questions from the hall right now?
I think Ralph has a question.
Ralph,
over here.
of course.
Thanks. Very cool stuff. I was wondering about M3, so the combination of mappings with the Monte Carlo and more on the Monte Carlo side. I mean, one of the key questions when one looks at, let's say, the extragalactic observations outside the H2 regions is the diffuse ionized gas.
Oh, yes, yes.
The leakage of ionizing photons in different frequencies. In principle, you can calculate.
Yes,
right?
in fact, that's one of the projects that we want to do, is to calculate the escape of ionizing photons, yes, with the models.
Can you do multiple sources? Let's say, can you take a batch of the galaxy, let's say half a kiloparsec cube, place a few H2 regions with multiple sources, and then reconstruct the overall radiation field?
Yes, you could, because it's scalable. It's 100, because it's fractal, it's 100% scalable. So you could do that. But again, we talked about this.
You would place, I don't know, 10, 20, 100.
Yeah.
Sources.
And the way the Monte Carlo models work is that we're actually calculating the amount of ionizing photons in the spectrum cell by cell. And so each cell is basically, its radiation field is the integral of all the radiation fields that are coming towards it, depending on whether it's directly from the ionizing source or whether it's been absorbed and re-emitted from another parcel of gas. And it can be from anywhere. So the way that's calculated means that you could have two ionizing sources on the same parcel of gas. You could have two H2 regions, and what escapes this H2 region could enter that H2 region if you allow that. And there would be really no change to the way the modeling is being done. That's one advantage of doing it this way with the cell technique. It's called, we're using basically following individual packets of photons.
Okay, cool. Thanks.
Just time for one more. If I may just ask you a question at the end. You mentioned about the dust attenuation. What particularly will you be doing? Is that also to do with the radiative transfer and looking at all the angles and the effects in the attenuation there?
Yeah, so we'd like to. So there's a postdoc in Australia called Andrew Battisti, who is calculating attenuation curves for various galaxies outside our Milky Way at the moment. And his plan is to use the radiative transfer code once we've put the new dust depletion factors in, because it's waiting for that, to help calculate attenuation factors better. It's more actually about what we're going to learn about dust and attenuation. The models I showed you didn't have dust in them at the moment. So these are single star dust free. The next step in the models is to do the dust, but for that that's why we needed to get those dust depletion factors correct, using the hyperspectral resolution simulations, observations rather. And so that's probably going to be another year, a couple of years away. Yeah, at least probably.
Okay, thank you very much. Look forward to seeing that.
I just have a question. Did you try these new models to reproduce the heavy element recombination lines? And if we have a better agreement now with these models, or you didn't try them yet?
We haven't looked at the heavy elements yet, no, but that's something we would like to do. I think we need some more students.
It's the last colloquium of the semester. I'd like to thank everybody in the audience for taking part and actively supporting this, and for all your discussions. I certainly learned a lot, also not only from the colloquium themselves, but also the questions afterwards. And thanks also to the people on the Zoom audience. We weren't always at the technical optimum, but I think it was a good experiment, and I think it worked very well that we were able to cater for the people who are not able to physically come from all the various locations in Heidelberg. Shortly, you'll be able to see all the colloquia of the semester, almost all of them, on this YouTube address. And I'd like to give special thanks to Yufeng Wang at the back here, who has been diligently doing all that for us and keeping things running. Again, thank you very much. And let us now especially thank Lisa for coming all this way, away from her very busy schedule, and giving us this beautiful insight into how to interpret spectroscopy and her view of all the things which are going to come from her group and indeed from her institute in the future. Thank you very much, Lisa.